Hi, I'm Rosa Catania, a postdoctoral researcher at the University of Leeds, United Kingdom, and have worked for the last 5 years on the development of hybrid physical material for the stabilization of membrane proteins.
I'm Paul Beales from the School of Chemistry at the University of Leeds. My group work on biological soft materials, in particular the engineering of membranes and vesicles. Here we've been developing hybrid membranes composed of natural phospholipids and synthetic diblock copolymers that can incorporate nature's functional nanomachines in the form of integral membrane proteins. We're developing these materials to support the functionality and enhance the stability of membrane proteins for future applications in biotechnology.
Hello, I'm Lars Jeuken from Leiden Institute of Chemistry, and I started collaborating with Paul because we were both interested to see if hybrid vesicles are biocompatible with membrane proteins. Using the model protein, cytochrome B03 from E. coli, we previously found that hybrid vesicles are not only biocompatible with membrane proteins, but could massively extend the longevity of cytochrome B03, which we found to be active even after a year of storage in the fridge.
Solid supported lipids membranes are systems where lipids membranes are absorbed in a planar configuration on a solid surface. Solid supported lipid membranes have a number of applications in spectroscopy and biosensing, and in this research we studied whether supported membranes could also be prepared from hybrid vesicles.
I'm particularly interested in how the physicochemical properties of these hybrid membranes can enhance the storage stability and functional durability of these membrane enzymes. Nature has evolved highly functional molecular nanomachines with properties beyond those we are currently able to design in synthetic macromolecules, and a large proportion of these natural molecular machineries reside within a membrane. The challenge is that these membrane proteins are difficult to handle and suffer from poor stability when taken out of the natural environment in a living cell. However, new materials that can overcome these obstacles may start to pave the way for these highly sophisticated molecular machines to be utilized within real-world applications in the near future.
I'm particularly excited about discovering how different the surface requirements are for forming solid supported hybrid membranes compared to traditional lipids membrane. Surface that worked perfectly for lipids bilayer turns out to be incompatible with polymer lipid system. So we had to rethink the surface chemistry from scratch. It was interesting to find that a simple mixed self-assembled monolayer of alkentiles and hydroxy-terminated alkentiles on gold provided the right balance of hydrophobicity and hydrophilicity to form stable hybrid membranes supporting active enzymes.
It was unexpected to see that membrane proteins with solid supported hybrid membranes were in fact not very stable. Although this was unexpected and of course not what we aimed for, it told us a lot about the interaction between membrane proteins and hybrid membranes, which we are keen to explore in the future.
So far, we only studied the behavior of membrane proteins in hybrid membranes with one polymer of a particular length. We hypothesized that the benefits of hybrid membranes can be further improved by optimizing this polymer length.
There's also so much potential to explore a wider range of membrane proteins with different functions to ascertain whether the enhanced protein's durability is a fundamental property of these materials or more specific to a subset of proteins with specific properties. This insight would enable these hybrid membranes to achieve their full potential in enabling membrane protein biotechnologies.
Thank you for listening, and we hope you liked the article on solid supported hybrid membranes.